Welcome everybody. Good afternoon. Thanks for coming. My name is Rafal Jaworowski. I'm daily doing development in embedded field systems. I'm trying very hard to do this in accordance with FreeBSD. So I'm trying to get most of my work to be connected with FreeBSD in the embedded fields. In the FreeBSD project, I'm mostly concerned with contributing to ARM and PowerPC-based systems. And I would like to tell you about some recent development that we've done in the past year on bringing FreeBSD to some new PowerPC platform, a very high-performance telecommunication system. So the presentation, I'll give some introduction on the terms and nomenclature that you'll be using, then I'll give some background on the PowerPC architecture, what it is and how it feels. And we will also see how previous situation with previous PowerPC support was at the time the development started. And then we will delve into some details of the 8572 device, which is the focus of our talk here. So, most concern will be about bringing SMP, because the machine is dual core, so we'll be mostly interested in how the SMP operations run together. And then I'll finish with a summary of the peripheral devices, how well the system is supported now, and what can be still improved, and what waits for developers because there's improvements. So starting with the definition, we will be talking about FreeBSD, right? So everybody knows what FreeBSD is. It's a great operating system. It runs on a number of platforms, and it's Unix. Among others, it supports PowerPC architecture, besides other known like ARM, Mix, and i386, PMD. So among others, there's PowerPC, which will be our most interest here. We will be talking about embedded systems. Embedded systems are unlike general purpose computers. They are usually dedicated to a certain task or certain well-defined set of tasks. They usually are part of a bigger piece. They are only an element in a bigger whole. And what will be discussed here is PowerPC architecture, which is a instruction set architecture definition. So it defines how a CPU low-level details are designed, how the cache are organized, how it will describe how many and what machine instructions we've got to do our work on. So historically, PowerPC started in the 90s. It was a consortium of companies, Apple, IBM, and Motorola. They rolled out a new architecture set definition, which was based on IBM's legacy RS-600 concept. And over time, it evolved, and we'll see that our variation found in this platform is a bit different than the traditional PPC. And currently there is an organization called Power.org, which is a non-profit group which shepherds the definition and further development of the architecture itself. It produces reference platforms. It manages, from a formal point of view, the directions of the architecture. And it covers many variations. We will see that PowerPC is not a single definition, but it's rather a group or family of specifications. Why at all being interested in PowerPC? It's basically very widespread. Actually, it might not be that exposed, but it's very much widespread, from embedded systems to game consoles. The IBM supercomputers, Blue Jeans, and others, they all run some derivative or modifications of, but still based on Power architecture. There's multiple vendors that produce that produce silicon that is compatible or compliant with the specification that the PowerQUICC provides. So users can choose from a range of vendors available in the market. So PowerPC is Freescale processor. It's load store approach. It can be superscalar and it's 32 or 64 bits. And what is particularly interested in the context of this talk is a book E variation of the specification. Is some of the modern modifications and some of the modern variation of the basic PowerPC definition, which is mostly profiled and is thought out to be dedicated for embedded applications. It is supposed to be binary compatible at the user experience level, although there are also some rough edges that this goal is not fully met in most of the cases, mostly because of the FPU, which I will discuss in details, but formally this new variation is supposed to be compatible on a user level. In reality, it's not always that sweet. Bookie highlights are the following. The main and foremost difference against the traditional PowerPC definition is the approach to memory management. And from this perspective, it looks like a completely different processor, basically, because the Bookie memory management is completely different than the traditional PowerPC. So we've got no more segmented mode of operation, and we do not have block translation as known and more established in the old PowerPC. There's only TLB-based, a purely TLB-based approach. We've got pages of multiple sizes, but there's no yield mechanisms at all. Some aspects of the exceptions area of the processor were reworked and extended. We will observe new class of exceptions added to the old approach, and there will also come new machine instructions to handle those exceptions. In the particular context of this talk and this work is Freescale implementation of this Bookie specification, and the exact core CPU that we'll be dealing with is E500, which is this vendor's implementation. One important thing that I had on the previous slide but didn't comment more is that Book E is, even though it's a specification, it leaves certain very lowest level details to the discretion of vendors' implementation. So, for example, when we talk about the MMU and the TLB, the specification doesn't have how many entries in the MMU should be, or how exactly should we retrieve or store data in the MMU. These very lowest level details are left to the vendor, and we will see that different producers would implement differently, which even within the same family group makes those processors a bit different. So the system that we'll be talking about is an integrated chip. So we will have one silicon piece that will have the core CPUs, and we'll have numerous devices around the CPU on the same physical part. That's a diagram that we can observe. So we've got this dual cores here, and we've got a number of supporting devices from accelerators to PCI, gigabit Ethernet. We've got memory controller integrated. We've got interrupt controller, UARTs, timers, GPIO. Everything is integrated in one small piece. The cores are driven 1.5 gigahertz clock, so it's a pretty powerful machine. We'll be seeing this picture a bit more often. So this was a summary of the system silicon. And now let's see how FreeBSD PowerPC port state looked like when we started this. So we didn't start from scratch. We had basic support for single-core E500 CPU already in the tree. This is the project that I was also involved with, and this previous work was really done from scratch. But when bringing up this dual core, we had a solid basis that we could continue to work for the dual core SMP work. So we had support for previous versions of the system in the tree already. So we had built environment that we could use right away, so we could produce a code for this target machine. We had a bootloader support. We had Pmap module that was developed at that time, which had only to be somewhat extended and adapted to the multi-core specification, but its basic logic and the basic support was there. We also had some rudiments, or not even rudiments, but we had some decent state peripheral support already for those SOCs. In particular, a couple of device drivers were already developed, like for the OpenPIC, the interrupt controller driver, the Ethernet controllers, and such. We have the device drivers hierarchy model already according to FreeBSD new bus paradigm. So we started the work around a year ago on this project, and it was FreeBSD 8 current at the time. We tried to not to diverge too much from the baseline, because when you are doing work on a board like this, it needs to be realized that it's not a quick task. It usually takes a couple of months. So you do not want your current work to diverge too much from the baseline like current, which is dynamically changing over time. So you would need to checkpoint with your baseline in reasonable frequency, because other than that, you just end up with very much differences in baseline, which are more difficult to overcome and integrate. So the environment was just in-tree toolchain, nothing special. We used what was available. The toolchain, in particular GCC and bin utils, were already able to produce proper machine code for E500 processes, so there wasn't any real work in this regard. We are using the traditional PowerPC ABI. You may also know that there is an extension to and a follow-up to this traditional ABI, which is embedded ABI. It has some different attributes, and it puts additional care about stack location and alignment. But we didn't have any particular needs to use the eABI, and by default, the toolchain produces binaries according to traditional. So we just went. What was the default? There wasn't any real need to use eABI. Yes.
If you implement eABI, are there implications to the kernel as well? Does that change the userland kernel interface?
Yes, I think so. Yes, you would need to recompile everything. Yeah. In terms of the details of getting 8572 up to speed, we first need to go through the Bootstrap phase, which is usually done by firmware. And in case of this system, this development system that we dealt with, it was U-boot based. U-boot is a very popular, especially in the PowerPC world, bootloader and firmware. So on top of U-boot, we had native FreeBSD loader running as a standalone application. It prepared the whole context for the kernel. It loaded the kernel into memory, prepared metadata, and it kicks off the kernel. So all those were already ready for use in this project, because we had, as mentioned, we have already completed the MP85XX, the previous versions of system. So these elements were ready for use. Also, many of the elements required for booting the kernel were already in there, like early CPU initialization, basic exceptions, interrupts. The bus-based operations, DMA, they were already implemented with PowerPC, so we didn't have any major modifications to this, only extensions. For example, on the bus-based interface, one of the peripherals that I was talking about, the encryption engine, it's got a requirement to do 64 bits I/O operations. So we needed to add in 64 bit width operations to the bus space, which were not in place, but they were quite trivial, so it wasn't any major extensions. Other than this, as mentioned, we have had the new bus hierarchy already designed, so we only fit into this. The main goal and the main focus of this project was about bringing the dual core operation and making FreeBSD PowerPC aware of SMP. There wasn't any FreeBSD PowerPC running on SMP machine at that time. So as far as basic nomenclature goes, when you've got multiple processor architectures, we can have a couple of approaches. One of is SMP, Symmetrical multiprocessing, and the other is AMP. We would only be focused and concerned about SMP. With the SMP, every processor in the system needs to be explicitly aware about the shared data, and synchronization needs to be explicitly done so that different processors do not interact with each other in a disastrous way. We'll have different roles while booting such a multiprocessor system. So we'll first notice there's a selected CPU that actually brings up the system and that then lets the other processors go. And this booting processor is called the Bootstrap processor, the BSD, and all the remaining ones are APs, application processors. Although, even though this naming scheme is kind of once the whole system is up and running, there isn't any difference between BSD and the APs. They are somewhat equivalent, although during boot up process, they need to be kind of differentiated. We'll see the details how it's done on this system. So, when filtering those generic terms through our specific system, we'll see that we've got a dual core, and core 0 would be the BSD, and core 1 would be the AP in our case. Freescale introduces the concept of core complex, which is the whole compound of the CPU, an MMU unit, L1 caches, and other internal CPU resources. So they call it the core complex. So in case of our system, we'll have two core complexes. The MMU is not shown here, but it's there. So it's part of the core, basically. So we would have two core complexes in case of our system. How such a dual core system is initialized and booted? We first need to know how the first instructions upon reset and upon powering on are executed. So, as similar to other systems and other processors, the CPU would fetch the first instruction from some pre-configured and pre-known location. Although the difference on the book E machines is that we do not have a traditionally known reset vector as in the old PowerPC. The CPU would just go to a certain location in memory and start to execute. It's not in the context of an exception. It's just a minor difference, but that's to also remind you about about differences in implementations, even in the same family of the architectural specification. So we could put the code from different locations. Typically, it is some read-only memory. We'll be mostly concerned about flash here. And as far as this booting processor goes, this core 0, it would execute the firmware code in the first place. So we would not care about that much of the first steps of initialization of the BSP, because mostly it executes the firmware code, U-boot code. So it's a bit beyond the kernel perspective. So although we would go to the details back again when we'll be talking about the APs which are started from scratch. So we'll look at this. Although as far as the BSP goes, it'll run firmware code, and we rely on U-boot to initialize this. So we will have core 0 executing the code, while the second core will be dormant. It will be held back, and it won't be activated at all. That's the overall approach here, and that's what our FreeBSD kernel expects from U-boot, that it wouldn't activate. If it activates, we would detect this and fail to initialize this, so we are not robust in such a case, which might happen. I mean, U-boot is a very simplistic environment, but it lets you do some things like directly. So you could manually start this second core. But anyways, so the way of the Bootstrap processor looked like generally like this. We had some assumptions about the underlying firmware, that it would set up environment in a specific way. So once those, among others, this is how the physical memory starts and where the kernel code and data are located. Once these are met, the FreeBSD kernel should be happy, and it would go on with the entry point routine, which sets up the CPU. It enables caches. It enables some features of the CPU, like prediction approaches, and some very close details of PPC CPU. It would initialize MMU in an early stage. It would set up kernel stack. It would initialize exception vectors, and it would then move on to a bit higher level initialization. Most of these steps are implemented in an assembly crafted routine because they are so specific to the CPU. They need to be crafted manually, and that's how it looks like. The early init is in assembly. Then we go to the C. Once we've got stacks set up, we can call C routines, which are much more readable and manageable, and they would finalize the CPU initialization. Then we go to machine event startup, which just goes all the way up to the scheduler. Although in an SMP system, before we let the scheduler go, we initialize the SMP subsystem, which brings to life the remaining APs, which we'll observe in details now it's done. So that's the way of the Bootstrap processor, the core 0. So some particular notes about book E processor behavior. The very far-fetching attribute or characteristic about this processor is that we've got MMU always on. There isn't anything like we cannot turn it off. That's how this architecture was designed. So we've got MMU always on. So we need to be sure that at all times we've got proper translations in the TLD present in order to execute the code or access any data that this code needs. So this is very important assumption and requirement, which we cannot get rid of. So certainly, if we do not have proper translation in the TLD, we will be receiving TLD messes which cannot be masked. We always need to surface TLD messes. Otherwise, the system will just hang because it will miss continuously. So when we are doing the MMU early initialization, we need to, on the DSP, we need to be especially careful because we need to, on the one hand, we need to clean up the MMU from the leftover and the remaining leftover that the firmware has left, right? Because the firmware also, because MMU is always on, the firmware also had to set its own translations for the code. So when we hit the kernel code, we need to wipe it out. Although we need to be very careful not to cut ourselves out from the code that is actually executing. So we employ a interesting but not very complicated technique of putting address spaces, because the book defines a number, actually 2 address spaces. So we flip the address spaces and set some temporary TLB translations, and we'll switch to this temporary translation, then we can kill all the other, then set up the target and final TLB translation, then switch to it and run from that finally. So this is how the BSP needs to be handled. After it's done with its lowest level initialization, we have kernel text, data, debug symbols, its internal structures that are built upon the initial setup. They all need to be covered by the TLB translations. We also are interested in getting access to the SoC integrated devices, right? As we had seen on the diagram, we will have a number of peripheral devices that will be memory mapped into the main address space in order to be configured and run. So we need to have them covered by the TLB translation. Everything else initially will be used clean. Now, at that time, we will also have PowerPC time counting facility set up, so we can do delays, we can do time counting. We'll also end up with L1, L2 caches enabled, so the processor is pretty much yes.
In the Bookie case, how does atomic instruction handle the cache consistency between different CPUs?
I will get to this. I've got a slide on this. So this would conclude a summary on the DSP behavior in this environment. Let's move on with the APs. So we have one DSP and one AP. As mentioned previously, the assumption and the requirement we have on the bootloader is that the AP would not be activated. In terms of Freescale nomenclature, it's in hold of state, which means that the CPU is kept as if it were at reset state. It basically is waits for us to let it go. The hold of mode can be configured at runtime. So the system designer can provide configuration word to the system, which is read very early from the address space. So we can really configure which of the core is held and which is activated. As we told, we assume that BSP on core 0 will be activated, and this is inactive. So that's the initial state of the AP that is inactive. It's in a hold of mode. In order for the AP to work, we need to understand another notion, which is boot page translation. Almost every critical aspect revolve about this MMU always on approach. So when we wake up the secondary processor, we need to make sure that it has a translation in the TLB in place to execute any code. And this initial translation is called the boot page translation. So we'll have some page that is initially translated, so we can run any code. And by convention, E500, when it's first powered up, regardless if it's BSP or the AP, it tries to execute its first instruction from the last word in the address space, and it tries to execute this. So it tries this, and the boot page translation by default translates the last 4 kilo page of the address space into the same physical address. So that's the default setup. The system wakes up, and we will see how to use those mechanisms to feed the AP, the secondary processor, with the code that we would like it to execute. The BSP had exactly the same behavior, but it was serviced, or it was handled by the firmware code. So the firmware's role was to provide at these addresses proper initialization code for the BSP. And in terms of SMP initialization, the BSP is already running, so we only care about APs. So we would now see how it's done for the AP. So this is a diagram of the situation. So we've got this last 4 kilo page accessible, and the CPU core would try to fetch this last instruction. And typically, this instruction at the last word is basically a branch at the beginning of this 4 kilo page, so we can have plenty of code to execute an initialized machine. So that's how it usually looks. So from the BSP point of view, when we want to bring AP into operation, we would modify this boot page translation to some code that we want the AP to execute. So we've modified adjust this translation and awake it. So it would feel this one from out of reset, and it would just start fetching our instructions. So that's the schema and basic idea how it's done. The secondary processor way of operation is initialization steps are pretty similar to what the BSP has done. So we would enable the low level of the CPU. We basically need to replay pretty much everything that the BSP has done, because they are separate entities. So, and we have noted that they've got separate MMUs, separate L1 caches, separate other resources. So we need to initialize them in the same way. So we would do pretty much the same. So we would initialize the MMU early, would set up stack, initialize the exception vectors, we would assign some per CPU resources, and then finalize the steps. And then when we're ready, we'll just try to go into normal mode of operation. We would let the AP just accept work. But before it happens, the AP waits for the BSP because there are some intermediary steps to perform. So the AP waits first signal to the PC wait for a signal from the BSP. And the BSP, in the meantime, provides the decrementer and time counting resources, all settings and time base, so that both cores have the same view of time counting state, and then it can enable its interrupts and start accepting work. So just before this, also an important item is that both cores have synchronized their TLB view of the system, so they can have the same view, and in particular, they both can access the SOC register, so they could do operations on the I/O in the same way. A couple of comments about helper tools and support from the hardware. That is what among others video was asking about. So in general, SMP is very difficult to realize and to implement if there isn't any hardware support for critical tasks. So First of all, there are atomic operations required, and PowerPC has historically always provided means to, with some elementary operations, to build more complicated atomic tools. So we've got this. It's very similar to what MIPS has. We've got this pair of instructions. One is load with reservation as its scope on a given location, and then is a complementary store, conditional store. So if when we do the load and we take the reservation, after some time we do a complementary store to this same location, and the store succeeds only if between those two points in time nobody has taken this reservation on this renewal, as it is called in Freescale manipulation. So we've got the means to basic atomic operations. There's also a number of mechanisms provided by the hardware to increase or enforce even data coherence between those two CPUs, their caches and main memory, and also between other external DMA masters that can do operations on the bus. So we've got a specialized module in the system that manages the coherency, so that L1 and L2 caches can snoop on the transactions, and if a DMA master is modifying a location potentially stored in the cache logic will discover this and behave accordingly, so it will invalidate or update its data that is cached. And similar mechanism is for communication between the CPUs themselves between their L1 caches. So whenever a given CPU is modifying a location that is potentially cached in the second CPU's cache, it will let know this other processor by hardware means. So the software doesn't need to do anything. Only it needs to mark such ranges that we are interested in synchronizing across CPUs that it's memory coherent when we do a TLB translation for this state. So that's basically how it's managed. And in general, all the memories in our system is marked as memory coherent. Besides I/O, which isn't a real memory, but all real RAM is memory coherent. Also, there are specific broadcasts being done in hardware. When a particular CPU does TLB or its local cache invalidations, the instructions are broadcast within the so-called coherency domain. So the other CPU's cache and the other CPU's MMU discover that such and such entry was invalidated, so it can act accordingly. And all these mechanisms work behind the curtain. So the software, the operating system is relieved from any intervention, basically. So this greatly simplifies and helps. Yes, that's the background. We've got a coherency module and we've got the caches. The important thing to note is that the coherency mechanism only supports data cache. The instruction cache is not hardware. And the coherency of the instruction cache is not hardware enforced in any way. So if you are interested in changing some locations containing code, executable code, you need to manually synchronize in order for the other CPU to discover the change in memory. A couple of comments still on the memory management, because it is the central item here, and it was the central concern in this development. So in the previous project, when the MPC85XX was first brought to life, we had come up with a separate Pmap module from scratch at all. So now with this dual-core SMP project, we only extended the Pmap module so it's aware of some parallelism and some atomicity required for full operation. But in general, the MMU consists of two subunits, one of which is completely managed by hardware, so it's not Pmap doesn't need to know about this and doesn't care. The second one is software managed, and it actually has two TLB units or two TLB tables. As mentioned in the beginning, individual book implementers, like different vendors, can do it differently, and this is only applicable to Freescale implementation of the E500 core. Other implementations, like you can find in AMCC or other vendors, they are different. They can have one TLB with different number of entries, different possible page sizes and things like that. So these parameters are relevant for Freescale. And even within a single vendor product, you can observe that even versions of the core, the same core, can have differences. Like, for example, the number of entries can vary from version to version. Newer versions have more TLB entries, like instead of 256, we've got 512. Things like that. We employ a very simple approach, very straightforward. The forward page table, two-level forward page table, and this is also different from the traditional PowerPC. The traditional PowerPC MMU, there was hardware requirements that the page table looked such and such. In the book E specification, there isn't any. The hardware doesn't impose any restrictions on the software, so we can implement the page table however we can, more like. And the traditional PowerPC had to be inverted page table because the hardware also imposed certain requirements per PTE, the page table entry structure. So the old PowerPC just less flexible. So the main challenges when we reworked Pmap module were we needed to deal with parallel TLB misses, because now we've got real parallel and asynchronously working MMU. So it needs to be noted that and remembered that this page table, the software page table that Pmap understands and deals with, is just one instance of this page table of the system, of the kernel, and each process has a separate page table. And we've got two separate physical MMU units, and they would miss on different addresses, different locations, and this needed to be synchronized. So we had to rework Pmap and rearrange certain areas of the code in order to be fully atomic and consistent. As mentioned, certain machine instructions are broadcast across CPUs, although there are also requirements that in hardware that we can issue only one such system-wide invalidation at a time. So we had to add a explicit spin log for this purpose in order to satisfy this requirement and things like that. Also, the overall logic of page table management was changed and optimized so we could better fit into multi-processor support. So this was the summary of the memory management and the core work. Now let me summarize the state peripheral devices that are integrated in the chip. So first of all, we've got 4 1 gigabit Ethernets integrated on this. So the driver for TSEC was already there. So we only optimized this and added new features. Actually, 8572 has an enhanced version of the chip, which is eTSEC, but it only adds new capabilities, and it's more performant. Other than this, it's backwards compatible with the old 85XX series. So we added features like polling, interrupt coalescing, VLAN tagging, hardware checksum, calculation, jumbo frames. The chip has a very interesting module. It's got a pattern matching engine, which is a co-processor sitting on the bus that can snoop on the bus, and you can feed it with regular expression defined strings or data that you are looking for, and it would do the search and find it in a hardware way. So it could be very efficient to do for applications when, I don't know, typical application for this is peak packet inspection, when the network traffic can be inspected on the fly in hardware, on a hardware level. The module also includes a decompression module, decompression unit, so you can decompress on the fly, even and look into packets or contents.
This access the buffers of the Ethernet controller? Can you basically get at the Ethernet traffic?
Yeah, it's a DMA engine. You can see whatever you want.
So you could actually use it for reassembly, packet inspection, and either.
Yeah, potentially. Yeah. So we developed a basic driver for this beast. So you can demo its operation. There's also an integrated security engine. It's compliant with Philips Open Crypto Framework. So we can do a number of algorithms already. And this one, as we talked during Philips' presentation, the engine is pretty complex, and it's got actually a subunit. It's got separate physically separate engines for doing hashes, for encryption, gas, for doing AES. They are physically separate units which can run in parallel. And this is hence we discussed making the OCF framework able of doing parallel work, because currently there is a bottleneck on the framework level. We cannot do operations on the engines simultaneously. Besides those, we've got PCI Express Bridge, which was also an existing PCI driver, only extended to work with PCI Express Bridge. The chip also includes a general purpose DMA engine. It can be used for any purpose. It's dedicated to any subsystem. It can transfer data. It's got the XOR subunit too, so you can, besides doing DMA, you can also XOR data, which can be helpful with I don't know, RAID or other applications. We've got I2C controller, which is also a new driver that's working with this. A couple of to-dos. The silicon, the system includes also an interesting unit, which is table lookup engine. It can do complex table lookup searches in hardware. So it's kind of complementary to the pattern matching thing. You can, if you've got like very complex rules for a firewall, it would greatly speed up things. It would accept certain in a certain formal description of the data of the table to search through, and it does it in hardware. There's no driver for this yet, so if anybody would like to do this, let me know. Also, the Ethernet controller has the precision time protocol hardware support. It can be utilized. There isn't currently any framework for this, but in FreeBSD kernel, but this can be a starting point for bringing the framework. Regarding sectors, a couple of algorithms still to be supported, like RC4 string cipher, built-in RNG. The acknowledgement, thanks for people with previous project, LM, to help me with discussions with Pmap and simultaneous misses. It was great. It was great to hear this. Smart Douglas from Freescale. Marcel implemented very early IPI interprocessor interrupt support for the OpenPeak, which was helpful because it was there. We didn't have to do with OpenPeak, which is the integrated interrupt controller on the chip. So, yeah, and a couple of people back home who did a great job on the peripherals here. And that's mostly what I have to say.
Yeah.
If there are questions.
I am interested in the effect of security engine hardware acceleration. That pull up the speed rather than core manipulation only. Yeah, from Philips session, that depends on the situation. If the core is very high speed, hardware acceleration is not affected. So I'm very interested in this case, security engine hardware acceleration.
That's pretty performant. I don't have any figures with me, but it was pretty good. I can send you some data because I've got some measurements back home, so I can provide you. But it was pretty good. The problem that we were observing is that if the system is doing like heavy IPsec transferring, it would be very much loaded with interrupts that the security module generates. That was our problem, and we tried to find out a way. This is why we brought this discussion with Philip about doing a polling mode of operation, because we had a great number of interrupts coming from the sec module. But other than this, it was doing pretty good.
Yeah,
But I don't have any figures with me, unfortunately. So
Thank you. I noticed that the security engine is not described in the data sheets. This is by design.
it should be.
No, I don't have the right data sheet.
Yeah, you know,
It's a Freescale data sheet.
yes, I wanted to tell you one. Oh, this slide. You see the E letter? There are two variations of the silicon. You can have one without E, which doesn't include encryption, or just a security accelerator at all.
So how much does it cost to buy this?
The SOC,
Well, no, this is
the SoC, it's pretty expensive. I mean, in small quantities, you can buy it for 200 to 150 USD. But it's a very high-end chip. Well, it's actually it's the highest chip currently available from Freescale. So it's really cute, and it's targeted towards high-end telecom applications. It's actually part of the so-called PowerQUICC family. Other PowerQUICCs have even integrated a dedicated RISC telecom processor that can do T1, E1, and other telecom specific interfaces. So it's expensive. So you wouldn't find it in at home devices, but you will find it in higher end networking equipment from different vendors.
Okay.
multiprocessor PowerPC machines, how the preemption is actually handled?
I didn't hear it.
In traditional, in PowerPC machine architecture generally, how the preemption is handled? It's disabled for kernel threads.
Oh, preemption.
Yeah.
Preemption is disabled, I guess.
Is?
It's disabled
Mm.
by default in our kernel config.
Okay.
We didn't test it much, so it's disabled. All right. So, if there are no more questions, thank you for attending.